So I'm going to focus on the questions 4 and 1, which were actually already discussed previously by Samantha. So on the low-grade gliomas, the cerebrum, the site question, cerebrum versus cerebellum. In the low-grade gliomas, we're talking about 40 cases, and the polycystic astrocytomas, which is a subset of these 40 cases, 27 cases altogether. And so I like to think that this is what we like to think that this is a difficult problem. And the way we approach the problem, at least in Genova, is from the point of view of what we call the rigorizing way of dealing with these huge dimensional problems using sparsity as the driving force. So this sparsity in this case is the prejudice we have about this problem. There are 54,000 gene expression, or actual probe set, let's say it out of but a huge number of expression, and we believe, and the doctors believe, that only a few, or a relatively small number, or fraction of genes are actually involved in the disease. So we're going to use this prior knowledge. So we don't know which one are, but we know that there are not 54,000 definitely. And so we have to go through a procedure able to select a few of those, a small fraction of those expressions. And the metaphor we're using is what we call the learning metaphor. So it's like having a system in which there are inputs and outputs. The inputs are the microarray, the gene expressions, and the outputs are, thanks to the clinicians, is that type 1 or type 2 is cerebrum versus cerebellum, depending on the problem, are the different subtypes. And so it's like having a bunch of examples, a microarray and subtype. And we want to be able to predict the subtype given the expression. But we're going to be a little more than that. Predict means we want to do it and want to be able to tell which one it is, not memorizing the solution, but generalizing, so the way humans actually learn. But we want to do a little more than that. We also want to select what are the features, what are the variables we are actually used to answer the questions. And this is what we call the sparsity. So in a sense, from the mathematical viewpoint, it's like looking for a bunch of numbers, the beta coefficients beta I. Each coefficient is attached to a gene expression, and we want to find only a small subset of this beta I. And we call it a small fraction. The rest will be 0, like irrelevant. And this, the coefficients, the indexes for which beta I is different from 0, will be given, or actually we gave those to our friends in Gaslini as a possible candidate signature of the disease, for example, in this case, of the site. And the way we do it is sort of quite different from classical statistics, I would say. And one of the main reasons is that despite the fact that we are dealing with a huge, or probably precisely for the fact we're dealing with a huge dimensional space, we don't want to go one gene at a time. And so what we do is we go multivariate. So this is 2-variate, but we're actually 54,000 variate, right? So we're going all the way up. And there are several reasons that we want to do that. And well, we might need more flexibility. And for example, we just learned, and you see an example of this, the normalization is one of the issues that could hide actually the different level of expressions of genes.